Welcome to the deep dive. Today we're jumping into something pretty wild.
Definitely sounds like sci-fi, doesn't it? Infinite realities, coexisting universes.
Exactly. But the mission today is to look at the science behind it, the physics foundation.
Right. And to really get into that, you first have to grapple with reality itself, at least how we observe it.
Okay. And we're using Anubhav Srivastava's book, Nothing Everything, as our guide here, specifically the segment called The Scientific Case for Infinite Universe Realities Coexisting.
That's the one. It really helps frame the core problem.
So let's start small.
Right.
Really small, subatomic. This is where things get, well, fuzzy, right?
That's the key insight. Down at the level of electrons, photons, certainty just vanishes. You can't pinpoint an exact position. It's fundamentally uncertain.
Why is that? Is it just our measurement tools?
Well, yes and no. The book uses a great analogy. Imagine trying to find a cannonball's position by just, tapping it lightly.
Okay, it doesn't move. You know where it is.
Right. But now try to tap an electron with something. The tap itself, the act of measuring.
It knocks it off course. Like hitting a ping pong ball with too much force.
Precisely. Your measurement becomes the disturbance, so physics has to shift from definite answers to probabilities.
Okay, so no certainty, just chances. This brings us to the math behind it. The wave function, psi.
Yep, the wave function TASAS. It doesn't give you the location, it gives you the statistical spread, all the places the particle might be found if you looked.
Like a cloud of possibility.
Exactly, pure potential. And before you measure, the particle is in what's called superposition, meaning it's sort of smeared out. It exists in all those possible states described by the wave function all at the same time. Reality is blurred.
Until you look. Then bang, it snaps into one definite place.
Right. That instantaneous jump from that wave of possibilities to a single particle-like reality, that's the measurement problem. And that's where things really diverge.
Okay, so how do physicists explain that jump?
Well, there are two main schools of thought. The traditional one, the Copenhagen interpretation, basically says the act of observation itself causes the wave function to collapse.
So looking forces it to choose.
Kind of. It forces reality to pick one outcome from all the possibilities. Simple, but maybe not the full picture.
And the alternative, the rabbit hole you mentioned.
That's the many worlds interpretation, or MWI. It takes a radical stance. The wave function never actually collapses.
Wait, never. So what happens to all the other possibilities?
According to MWI, they all happen. Every single possible outcome described by the wave function becomes real.
But in separate parallel universes.
Exactly. The universe splits, or branches. If an electron could be spin up or spin down, the universe branches into two, one where it's up, one where it's down.
So there's universe for every single quantum choice. An infinite number of me's living out every decision.
That's the staggering implication, yes. It flows directly from taking superposition seriously.
Does it need a conscious person, like watching for this split to happen?
Good question. Not necessarily. That's where quantum decoherence comes in.
Decoherence.
Yeah, it basically says the environment itself, stray photons, air molecules, any tiny interaction acts like an observer. It forces the system out of superposition.
So the universe itself sort of measures things, or causes the branching.
In a way, yes. Long before a scientist shows up, the noise of reality is enough. A conscious observer isn't always the trigger.
Okay, that makes slightly more sense. Maybe. Now there's one more really weird piece, right? Quantum entanglement.
Oh yeah, the spooky action at a distance, as Einstein famously called it. Not fondly, I might add.
This is where two particles are linked.
Linked in a deep way.
Yeah.
If you measure a property of one, like its spin, you instantly know the corresponding property of the other, no matter how far apart they are. Miles, light years, doesn't matter.
Instantly. Faster than light.
It seems that way. The connection is immediate. And the source, Srivastava's book, points out that this really makes you question space itself, if the connection ignores distance.
Maybe distance, space as we know it, is sort of an illusion.
That's the profound implication it suggests, yeah. It challenges our fundamental understanding.
So, wrapping this card up then, these core ideas, superposition, the wave function collapse, or lack thereof in MWI, these aren't just philosophical musings.
Not at all. They're the direct results of quantum mechanics experiments. The science itself forces us to consider these possibilities, like many worlds.
Yeah, this is really just setting the stage, right? We need to delve deeper into Copenhagen versus many worlds next time.
Absolutely. There's a lot more to unpack there.
But just to leave everyone thinking, that entanglement thing, if measuring one particle instantly affects another light years away.
What does that truly say about the fabric of space and the universe's ultimate speed limit? It's a deep mystery.
A mystery explored further, again, in Anubhav Srivastava's book, Nothing Everything. The mind-bending philosophical theory of everything definitely gives you something to ponder.